Start. Okay, fantastic. Just to let you know, the lecture is being recorded. Morning, everyone, again. So as I mentioned just before the start, this week and next week we will focus on optimizing with Python. Today we will learn the basics of how it works, the optimizer in Python. And on Wednesday and Friday this week, first we will learn, we will practice more to solve extra questions with the optimizer that I will introduce to you in a moment. And next week, what we will do is we will have data sets that we will import to Python first, that we learn during Python workshops, and then we will solve them using optimizer. I will refresh your mind on how to import data set as well. But this is the reality in real life that we have data sets, big data sets, usually that you cannot work with them manually, or you cannot write the models manually yourself, or you just want to avoid any sort of like mistakes. That's why we use data sets to import the data and then solve the problem. Okay. That's a quick introduction. As I mentioned, for this week and next week, please bring your laptops for the workshops as we'll write codes together. Now, let's start our lecture for today. I will use Anaconda as the platform, as the IDE for Python. If you remember during the Python workshop also, I mentioned that you are more than welcome to use whatever that you want. So you can use Anaconda, you can use Spider, you can use VS Code, you can use Jupyter, Colab, and also I recommended actually use any online platform that you can integrate AI with it. I know Anaconda also allows you to integrate AI with your platform, so that when you're writing code, you can ask AI to debug the code for you. You can get help from AI, which is very useful. So feel free to use whatever that you want. I use Anaconda, and this is the one that I'm more fluent with. So if there is any questions regarding Python in Anaconda, would be more useful. Well, it is also worth to mention that they're all the same syntaxes, right? So if you know Python in Spider, you will be able to use Colab or Jupyter as well. They're like very, very small differences that you can easily figure out. For Anaconda, you can use the link which is in the slides to download it. It is compatible with Windows, macOS, or Linux. It includes several packages for scientific computing already. So I'll show you a few of them during Python workshop, NumPy, Pandas, and many other packages that you can use. It supports easy installation of Pyamo and Solver. So Pyamo is the optimizer that we will use to optimize to solve linear programming models. Install Pyamo solvers and other packages. You can use it. You can install them simply. That I will show you a few steps in the next slides. But if you're using terminal, and many people do, you can just use the commands that I put on the slides. Basically for your computer. There are different optimization packages that we have in Python. A few of them, quite a few of them. Each of them is designed for a different purpose. Pulp is the first one, PULP. You can see the LP at the end. This supports concrete modeling with linear programming and mixed integer linear program model. Linear programming is the one that we already focused on. We covered the first 2 weeks, and mixed integer linear programs are the ones that we will cover on weeks 5 and 6. Both of them are linear programming. They're just different conditions on the decision variables. That's all that we, the biggest bit, I mean, the main difference is there. Pulp is something that you can use to solve linear programming models and also mixed integer linear programs. Apple Pie is another one, APLE Pie. It supports concrete modeling for linear programming and mixed integer linear programming models again. We have PyMath program, we have PyPLG, we have Cplex, and we have Groby. Python interfaces for scientific solvers, specific solvers too. So you can use any of these solvers within Python. Some of them are open source, like Pulp and Pyomo, the one that we will also focus on. Some of them are not open source and free. Cplex and Groovy, both of them are like amazing, but they're not open source. They're not free for academic purposes. They are free, both Groovy and Cplex. But at the end of the day, if you work in industry, if you want to use them, you have to pay for the license, and they're not cheap or expensive. The last one is Pyomo, the one that we will use as a part of this module, which supports concrete and abstract modeling for linear programming, mixed integer linear programming, nonlinear programming models. I'll explain you what is concrete and abstract modeling today a bit, and more in the workshops. But you can see here that Pyomo is more comprehensive. Even though we will focus on linear programming, mixed integer programming, and nonlinear programming as a part of this module, there are other sorts of like models that Pyomo can solve, but you can't use Pulp for them. For instance, nonlinear programming is the biggest one that you can't use Pulp for that, but Pyomo basically is comprehensive enough to solve any sort of optimization models that we have. Quadratic programming can be nonlinear programming, as I said, so on and so forth. There are modeling extensions for stochastic programming, bi-level, and MPEC modeling as well. So you can see here that Pyomo is the most comprehensive one that we have. It is open source. So in future, when you know how to model linear programming or mixed integer linear programming or nonlinear programming with Pyomo, there are loads of, as it is open source, there are loads of documentations that you can find, and easily, if you need to solve stochastic programming or bi-level programming, easily you can use Pyomo to solve them. Now, where does Pyomo come from? Pyomo basically was sort of like created in San Diego National Laboratories. It is a Pythonic and language, and it is open source. It's very important. When it is open source, it is free of charge for everyone, which is amazing. And also there will be like developments by many people around the world. It's solver agnostic. There are lots of solvers that we can use to solve the problem. So remember that we started from the beginning that we wanted to translate a written statement to mathematical formulation to be solved manually using graphical solution method that we saw last week. If you have two decision variables, essentially. And then we said that in the next step, we want to translate this mathematical formulation to a language that computer understands. For us, it's Python. Pyomo is basically the translator that Python understands from mathematical formulation to Pythonic language. And then a solver will be used to solve the problem. Okay, so these are the steps that we have. So there are different steps that we can use here to solve any linear programming model. GLPK is one of them. IP-opt is another one. Groovy, Cplex, as I said, some of them are like free of charge, open source, some of them are with license. It has a high level of API, which is really important. Extended documentations exist that you can find. There is a nice book that also put on the reading list on modules webpage that you can find it. The book is also amazing. Some of the lectures and some of the notes that I have from my lecture today are from the book that I got, because book is amazing. There are loads of nice examples that we can find. As we said, it can solve advanced optimization problems, linear programming, nonlinear programming, integer programming, mixed integer programming, stochastic programming, bi-level, so on and so forth. Question here, I think there should be space between conda and install for installation script. Okay, conda install, yeah, that's sensible. So on a slide, the first slide, the last two commands that I'll have for terminal is conda install. There is no space between them. Not is right. Normally we have space before the command and install. So it is I presume you already tested it, and you said that there should be a space. Okay, so there is a space between conda and install. I will fix this before and then update the lecture notes on the web page. Thanks for letting me know. Now, how do we install how do we install Piamo in Python? So that was Conda that I can use. It might be a bit like lengthy. If you have Python, that I presume you have, because you all were in the Python workshops I had on week 0, simply you can use pip install Piamo. So pip is a command that we use in Python to install different packages that we want. We'll do it. I guess I showed you for pandas as well, right? For pandas, we showed you that you can use pip to install pandas. Now you can use pip install Piamo to basically install Piamo on your computer. So remember that we have this part of the user interface. Spider is the one that I'm showing here. As you know, there are loads of IDs they have out there. That's why I'll just show you one of them. So here simply in the shell, if you just write pip install Piamo, it takes a few minutes or moments that then you will have Piamo installed on your computer. Once a package is installed, you don't need to install it again and again. So once you have it, you have it. So there is no need to, unless you remove it from your computer. So you don't need to have pip install Piamo as a part of your code every time that you run your code. Once you did it, you'll have it. So for me, I will show you at the beginning when I started to write the code, because I have Piamo installed in my computer. When I write pip install Piamo and run this, I'll get requirement already satisfied because I already have it. Okay. Piamo objects exist within the Piamo environment namespace. So if you remember again from pandas, with pandas, you have to indicate if you're writing something, it is from pandas, right? So if you remember, we gave the nickname PD rather than writing pandas every time that we are writing something because it was shorter. To just indicate and let Python know that we are writing something, an object which is from Piamo environment, we have to use piamo.environment namespace. This is the way that we do that. For instance, if we want to create a model, which is a concrete model, first we have to import, just do laser point. So first we have to import Piamo environment, as we do here. And then when we want to just create a model, a concrete model, we have to indicate that this concrete model is from Piamo environment. This is an object from Piamo environment. That's why we have to write it as piamo.environ dot concrete model. So this is exactly the way that we did in NumPy and random, if you remember. In random also, we first imported random package and then we used it to create something. With Pontos also, we first imported Pontos package and then with the package that we had, we created an object which is called like concrete modeling, or it was like importing something to our let's say it was basically importing a data set to our computer or to the code that we have, right? So that's exactly the same. Whenever you want to create something which is related to Piamo, you have to indicate that it is from the this is an object from the environment that we already imported. But you can see that you have to write it every time that you want to create an object related to Piamo, right? It's piamo.environment. Yes, you can use a suggestion from Python. You can use tab to just have it, but still, with pandas we did the same. We assigned basically a nickname, and then again we did the same. If you remember, so it was import pandas as PD, and rather than writing pandas every time, we use PD. You can do the same here. Import piamo.environment as, and then you can assign a nickname that you can use it in your code. It can be PYO, for instance, POY, or whatsoever that you want to call it, right? This is a way. There is another way that you can just skip this this step of giving the name every time that you want to do. So rather than import in this way, import the environment, what you can do is from the environment that you have, which is pyamo.environment, import star. This basically imports all objects related to Pyamo or the package that you're talking about. I'll show you when we start to write the code. In this way, you don't need to indicate that concrete model that we have here is an object of the environment that you imported. It will guess it itself. Okay? You will always see there will be a warning that, oh, you're importing, you're using concrete model, which I don't know which it is, what it is, but it might be from the package that you imported. You will see the warning. I'll show you in a moment now. To clarify, Python specific syntax, Python symbols are highlighted in green. It depends, it may depend on your color coding of your script, Python or Spider, but for me it's green. We have concrete and abstract models. So let me quickly explain you what do we mean by concrete or abstract models. We'll work on both of them. I'll show you both of them, basically. But we are always expected to write concrete models as a part of this module. Okay? Concrete model is a model that you know all constants, coefficients, values, right-hand side, left-hand side, everything is first created in your code, and then the model is formed. For instance, consider the paint problem that we have. In paint problem, we said that we are selling two paints with different prices, 2K, 3K, and 2K. We have two raw materials. From each of them, we have like 6 and 8 units respectively from raw material 1 and raw material 2. We know for each of the paints or products how much of each of the raw materials we need to mix to get the product, right? Everything was known. So what we did basically, we formulated the problem as like 3x1 plus 2x2 subject to 2x1 plus 1x1 2 less than or equal to 6 and other constraints. So in Python also, we first create the data, which is the price for product 1 is 3,000. The price for the second product is 2,000. The available units, the number of units available from raw material 1 is 6. From raw material 2 is 8. And then we build the model in Python. This is concrete. You know first what are the values, and then you create the model. This is unlike abstract model that you don't need to indicate the numbers first. So you can say that you will have a problem with n different products. You don't need to indicate that you have 2 paints. You tell that the price of the first product is P1. You don't need to say that it is 3. The price of the second product is P2. You don't need to indicate it is 2. The available resources for raw material 1 is R1, for instance. You don't need to indicate it is 6. So you basically create your model as P1x1 plus P2x2. And then whatsoever is the left-hand side less than or equal to R1. This R1, P1, P2, they are not decision variables. They are some scalars which will be given later. It becomes an abstract model. So concrete model, you have to give everything first, build the model, solve it. In abstract model, you will create a parametric model. You will give a P1 there, which is the price of product 1, which can be 3, which can be 2, which can be 4, which can be 5. Later, you will indicate that P1 is equal to now. P1 is equal to 3. Solve the problem for me. Okay? So this is an abstract model. Basically, you will create a parametric model that you can solve for different values of each of the parameters that you have in the model. Okay? So this is the difference between concrete and abstract model. As I said, we'll focus only on concrete models as a part of this module. There's some core modeling components that we have in PMO. VAR with capital V. So remember that everything is case sensitive in Python. So uppercase and lowercase, they have different meanings. So VAR, which is the first part of variable, basically, shows us the variable, decision variables. V is uppercase. The VAR component is used to represent optimization decision variables. PMO supports continuous, integer, and includes several predefined domains that we will see now. So we have continuous decision variables, if you remember. Integer decision variables, slightly told you in the first week that if you're producing cars, you can go with like 1.2 cars. It's either one car or two cars, right? So they need to be integer, that we will learn on weeks 5 and 6. There are some predefined domains that we can use here. If you remember, for linear programming models, we need decision variables to be first continuous and second non-negative, right? We will see there are like predefined domains just to indicate that this decision variable is continuous and also non-negative. The second one is objective with uppercase O. Again, you can guess. The objective component defines the function to be optimized by the solver. So you have to give your objective function. First, you create your decision variables. Remember the decision variables, when you have them, you can write the objective function, which is a function, a linear function of your decision variables. This component contains the expression used to define objective function and a flag to indicate that if you're maximizing or minimizing the problem, we should call it a sense. So you will have the objective component in PIAMO. It needs two arguments. The first one is the expression, which is the function of decision variables, the objective function. And secondly, you have to indicate if you are maximizing or minimizing this objective function, which is called the sense. The third one is constraint. Constraints are used to define additional restrictions on the decision variables. Remember that we seek to optimize an objective function by modifying a set of decision variables within a range which is subject to some constraints, right? When you have decision variables, you are able to write the objective function and constraints. So constraints here should be functions of your decision variable on the left-hand side and a value on the right-hand side. The constraints component contains expressions and the appropriate relational operator. PIAMO supports equality or inequality constraints. So for equality constraints, we need to have double equal sign, and for less than or equal to or greater than or equality, as always in Python, we use greater and then equality, or less and then equality sign to make sure that the constraint is less than or equality or greater than equality. So again, for the constraint, we need to provide expression, which is a function of decision variables, and then you have the sign, and then you have your value on the right-hand side. Expressions, the expression component can be used to create the PIAMO expression that can be reused in different parts of PIAMO model. So if you have a function which is used in different parts of your model, or different models that you're writing the same script, you can create one expression, and then you can use named expression, obviously, and you can use it in different parts of your code and change the parameters or constant that you have within the function. It is similar to, you can guess, this is similar to a function that we would write in Python. And finally, we have the set. The set is the component. The set component represents the collection of data that can include numeric, for example, integer or continuous or real, or symbolic, which is like string elements. They're most commonly used to define valid indices for other components. Several common set operators are also supported within PIAMO. So basically, set is, we will see one of the examples that we will work on this week in Virtual, that you have a set of, for instance, for paint problem. In the paint problem, we have two products, right? Paint 1 and Paint 2. It's a set of products that you have, Paint 1 and Paint 2. You can create a set in your code, and then you can use this set in different parts of your model, because your set is Paint 1 and Paint 2. You can define your decision variables based on this set. You have Paint 1 as the first decision variable, the second one Paint 2. You can use this in your objective function. You can use this in your constraint. You won't use it a lot, to be fair, but it's something that is good to know. Right. Any questions up to now? That's good. Now, So let's see how it works, and then we will write it properly in Python. We first start by importing objects to Python. So from Piamo dot environment import star, which means that all objects will be imported to your computer for the time being. This is not like pip install, right? For pip install, once you install something, you have it there, so you don't need to use it again or install it again unless you delete it or remove it from your computer. For import, you have to do it with your code. So whenever you're running your code, you have to put this import to make sure that these objects are imported. So all Pyamo model starts with this, that the Pyamo environment is first imported. It tells Python to load all Pyamo modeling environment that you have. Second, you will start with an empty model. So first, you start with an empty model that should be filled with decision variables, objective function, and constraints. As we said, we only focus on concrete model because in the cases that we are working on, we'll give the data first, and then we'll build the model using the data that we have. Model equal to concrete model. Concrete model, C is uppercase, M is uppercase. It is equal to model. This creates an empty sheet basically as the model. This model here, the first one, is a local variable. This is the name that I'm assigning to my mathematical formulation. Oops. It is model. It can be a profit maximization. It can be cost reduction. It can be the name of the company. So whatever that you want, that easy for you to understand. This is local variable to hold the model you are about to construct. So we created this model, which is empty, and then we are going to construct the model and thanks to one not required by convention, we use always model. So it can be model one, model two, model profit, model cost, or whatsoever. But as I said, it's completely up to you. You can use any name that you want. If you choose to name your model something else, you will need to tell the Pyamo script object name through the command line. So if it is another name, you have to make sure that you use the same model when you are constructing or adding stuff in your script. Concrete model, create an instance of a concrete model. Concrete models are immediately constructed because we have the data, we have the input. We don't need to wait for the data to be given. Data must be present at the time components are defined. So you have to indicate how many decision variables you have. With an abstract model, you don't need to indicate how many decision variables you have. You just can tell that you have n decision variables. This n can be 2, this n can be 5, this n can be 10. With a concrete model, you have to indicate what is the exact constant for the specific decision variable. Decision variable 1, x1, its constant is like 3. With an abstract model, you don't need to indicate it is 3. You can give just p1. P1 can be 3, can be 5, can be 10 later. So data must be present when you are defining the components for the problem. The second step. So we imported Pyamo, we create this empty model. Now we are going to construct the model. How we are going to construct the model basically, in the first step, you have to define the decision variables. When we were translating the written statement to mathematical formulation, again, we started the same, right? We first defined the decision variables, and then we had the objective function, we had the constraints, so on and so forth. So we do the same here because if you don't have the decision variables, you are not able to define the objective function. If you don't have the decision variables, you're not able to define the constraints. So first, we define the decision variables. Now, model dot x underscore variable. Model is the name of the concrete model that we created. If it was model profit, for instance, you have to use model profit here. Model dot, this means that hold on, I'm going to add something to this concrete model, which is called model. This dot means I'm going to add something to the model, the concrete model that I created, and this name is model. X underscore variable is the name of the thing that I want to add. This is like model again. X variable, it can be paint one, it can be product one, it can be city one. So it doesn't really matter. It's something that you are going to assign. It's not something which is an object from Pyamo. It's up to you. Model dot, hold on, I'm going to add something. x underscore variable. What is the name of the thing that you want to add? It is x underscore variable equal to. Now you have to define what is the type of the thing that you want to add. Are you going to add a variable? Are you going to add a constraint? Are you going to add an objective? So by saying that it is VAR with uppercase V, you're indicating that you're going to add a decision variable. What sort of decision variable it is? It is an LP that we are working on. For LPs, we know that the decision variables are continuous and non-negative. Within gives you the chance to define basically a domain for your decision variable. We said that the domain of our decision variable is non-negative continuous. Continuous decision variables in Python are real numbers, right? Non-negative written in this way, non-negative reals basically indicates that your decision variable is continuous and non-negative. I'll give you a few predefined a table which contains all predefined domains for the decision variables. So here, model is a reference to the blank model that I created. The dot after that means that I'm going to add something to this model. Next one is the thing that I'm adding, and the thing that I'm adding is called this. So that's the name of the thing that I'm going to add. Next, VAR is basically, this is a PYAMO function for marking decision variables as we discussed. Within is optional here, by the way. You don't have to define the domain of your decision variable here. You can go and add a constant, right? Because x1 is greater than or equal to 0, or x underscore variable is greater than or equal to 0. You can add a constraint, but it's always easier if you can use built-in functions of PYAMO to use them rather than using constraint to essentially indicate something. So within is optional and sets a variable domain. Domain is an alloys for within that I will show you. You can either use within or you can use domain. So here, the name you assign to the object, assign the object to, the name that you are assigning to the object becomes the object's name, and it should be unique within your code. If you have two models, you have to make sure that within one script you have model 1 and then model 2. If this x variable is for model 1, you have to make sure that you're just assigning it to model 1, the name that you create. Okay, so this non-negative real, basically, I said that this is the predefined domain of the decision variable that we have. There are several predefined domains that we have. So you can see in the table that we have any, for instance, this is another domain that we can use, and it's any possible value that it can get. It can be positive, negative, real values, etc. But the ones that we use most are these ones: real numbers. It can be it is continuous, but it can be negative as well. Positive reals, any real numbers which are like greater than 0. Non-positive reals, any negative values for negative and 0 as well. Non-positive, so it shouldn't be positive basically. Negative reals, non-negative real is the one that we use a lot. The set of all non-negative floating points values. So float variables, if you remember from Python, they are real numbers or they are continuous variables, and it is non-negative. This is exactly what we want for our decision variables. On week 5 and 6, we will focus on non-negative integers as well. So it is written as non-negative reals. When you start typing non, you will see the suggestion for everything that exists in PYAMO, and you just choose the one which is the correct one for you. Just make sure that if you're typing yourself, none has a capital N, uppercase N for negative, and it is reals. So there is S at the very end. Binary is another one that we will use. If you remember, true or false, 0 or 1, or the sort of like binary decision variables that we had as like the outcome of if conditions as well, right? Again, we'll work on this when we're on week 5 and 6. Just checking the chat box. Since you said there are domains, can you use domain? I will show you in a moment. Yes, domain and within work exactly the same. There's nothing which is different. So it comes to your point now, the question. So again, this is model dots hold on, I'm going to add something to the model that I created. X underscore variable is the name of the thing that we are adding. The type is var, which is a decision variable. Now we can use within or domain, bounds, or initialize. So there are different things that we can use. Domain and within are exactly the same. So for within non-negative, you can use domain non-negative reals as well. So instead of writing within non-negative reals, you could use domain equal to non-negative reals. Bounds or another sort of like thing that we can essentially indicate what is the boundaries of the decision variable that you have. When you have non-negative continuous decision variable, basically it is greater than or equal to 0. With bounds, you have to indicate the lower bound and upper bound on the value of the decision variable that you create. When you have non-negative decision variable, this means that it can be at least as 0, but it can go further as much as it wants, right? So it can go to infinity, which doesn't exist. That's why we have 0 as the lower bound, and then we have none, which is no upper bound on the value of this specific decision variable. So within domain, we'll use one of these ones which are in the table. With bounds, you have to give the lower bound and upper bound on the value of decision variable. If it is non-negative continuous, basically, you can see, by the way, when you have bounds and you have lower bound and upper bound, you don't need to indicate that it is continuous. So by default, PIAMO presumes that decision variables are continuous unless you define otherwise. Okay, so with bounds, you don't need to tell that it is continuous. It's just 0 as a lower bound and nothing for the upper bound. So we added our decision variables. We're good to create our objective function and constraints. Again, model dot, hold on, I'm going to add something. What is the name of the thing that we are going to add? It's objective, or use a nickname, which is OBJ. Could use profit. What is the type of the thing that you're adding? It's objective with uppercase O. Now, for objective, if you remember, we have two components. First, you have to give the expression. Second, the sense. The expression here is the objective function that we want to add. We'll see in a moment what it is. Sense, it is minimize or maximize with Z, not S. It's American English, not British English. So sense is minimize or maximize with Z here. So minimize with Z, maximize with Z. It's American English. Now we have defined our decision variables, let's say X and Y. Two decision variables for the model, paint1 and paint2, defined as X and Y. Model.x, model.y is the variable. Both of them are non-negative reals. So I use bounds for X, which is 0 to none, and I use within, and I give a predefined domain, which is non-negative reals for Y. So I have two decision variables here. My objective function here is 2x minus 3y. So what I do is basically model.ob is equal to objective. The expression is 2 multiplied by model.x minus 3 multiplied by model.y. You can't use x and y separately because x and y are just used for the sake of illustration. For your model, it is model.x. The reason is, as I said, you may have different models in the same script. You have another x, which is another decision variable for another model. So you have to make sure that you indicate from which model you're talking, from which model this x, this decision variable comes. So that's why you have to indicate the model as well, model.x, model.y. And then you have to indicate the sense, which is minimization. Again, by default, PIAMO considers all models as minimization. If you indicate it's maximization, that's all right. Otherwise, if you don't have sense equal to minimize, you'll always treat the model as a minimization problem. Now, constraints. Model.constraint underscore name. It can be raw material, for instance. Model.constraint raw material 1. What's the type of the thing that we are adding? It's constraint with uppercase C. You have to give the expression again. I'll go to that one again. Expression can be an expression or any function like object that returns an expression. So you may write the function here yourself, or you may create a function up there, which for you creates the function, the function of the constraint, which is a function of decision variables. I normally tend to put the constraint here rather than creating an object that we learned in Python workshop and use it here. I'll always write the function because if there is any issue, easier I can handle it. Unless the problem is so complicated and there are loads of constraints, and I don't want to have a messy script. That's the only time that I don't use that. Now, again, let's say that we have the same decision variables, x and y, both of them are non-negative reals. I want to write the constraints that we have. Let's say we have a labor constraint, which is model.labor constraint, named it, the type is constraint. The expression here is equal to minus x plus 2y, and it is less than or equal to 10. Simple. The expression is the function, the left-hand side, the function that you have on the left-hand side of the constraint, which is a function of decision variables. And on the right-hand side, you have the value of right-hand side, which is 10, for instance. The second constraint is capacity constraint. Expression is 2x minus y, which is equal to 30. So simply expression equal to the function, and then you have your right-hand side, and you have to add the sign as well. It is less than or equal to, less than or equal to. If it is equality, equality, or greater than or equality, it can be. Okay. There are other ways of introducing adding constraints. One, you could see that you can add the constraints one by one. This is the way that I use. But you can use a list of constraints as well. So model.limits, basically limits is the name that we are assigning. And I said that this limits is a list of constraints, which is constraint list. And then for each of the constraints that I have, what I do is I just add it to the limits, the name that I gave. So I could name it model.constraints and then model.constraints.add, and then I would add the constraint of the problem one by one. So it just makes the code cleaner, to be fair. You may have several capacity constraints. So you may write model.capacities and then add only capacity constraints. You have demand constraints, different demand constraints. You may create a constraint list only for demand. So it depends on the type of the problem that you have, but there is no harm in adding all constraints one by one, as I did in the previous slide. Do we have the model? So what we did here is we started by creating a blank model. We created our objective function, decision variable, objective function, constraints. Now we have the model. Now we have to solve the problem. To solve the problem, basically, we need to first indicate which sort of solver we are going to use. We say that it is an optimizer. OPT is the name that I'm giving. This is a local variable. Solver factory is an object from Python, from PMO. And now I have to indicate the solver that we are going to use here. GLPK is one of the solvers which solves linear programming models. It is super simple to use, super simple to install, and it is open source. GLPK in quotation, and it is green. This is our solver. This is a solver. There are different solvers that we can use in PMO with within PMO, Groby, Cplex, CB, C, IP opt, etc. GLPK is one of them that is open source and can handle linear programming and mixed integer linear programs. Once we have the solver, you use this. So this OPT is the local variable that I created here, dot solve model. You have to indicate which model you want to solve. Once you did this, you will have your model solved. As output, you may get different status for your model. Your model can be okay, which is the normal termination. There might be a warning, which is there is an issue, there is a warning with your code. Error, there is an error that we will see. There are different like sort of things that can happen as the error. Aborted is that you interrupt the code and stop the code. Unknown is really tricky because you don't know what happened there. There are termination conditions. So it was the status of the model, and there are like termination conditions. A model stops working if it finds the optimal solution. That's the first one that we like a lot, right? So if the optimal solution is found, then the model stops and it gives you the optimal solution. If you remember from outcomes of LP, for instance, if it is unbounded or it is infeasible, again, it will terminate and gives you the report that your model is basically unbounded or it is infeasible. There are lots of other termination conditions that you can see here. Okay. Now let me quickly move to Python. This is basically our paint problem. only 1.9 here is 1. And I made the coefficients of the decision variables in the objective function as 3 k instead of 3k and 2k as 3 and 2. So if you remember, from Anaconda you can launch Spider that I do here. In the meantime, I'll just check the chat box since there are several solvers. So each of them does, I have the list right in these slides. The question is how you know which solver you have to use. GLPK is used for linear programming, mixed integer programming models. CBC, IP are used for nonlinear programming. Groovy and CPLF can deal with any of them, but they are not open source. So, and you can find in the book as well, there are like different different applications of each of them. Based on your need, you have to choose one. So let me launch my Spider. What is the difference between globally and locally optimal? We'll discuss this in nonlinear programming. Okay, there we go. Couldn't find it. This is Python. Okay, I'll come back here. There we go. Let me open a new script. Okay, so this is my Python simply Spider. So this is what we used to do, right? First, from piamo.environ import store. This imports everything, if you remember, right? This imports everything that we have. So if I run this, you can see in the variable explorer. You want me to increase the size of the font? 24. Okay, it's better now. So you can see there are loads of things like maximize, minimize, integers, non-negative integers, etc. Everything is imported. Okay. Now model is equal. So first, concrete model. You see that when I started to write CON, I have loads of suggestions. I just click on this, and now I have it. First, you have a warning here. It says from Pyamo environment import star used, unable to take undefined names. It says. Now, if you go to the next one, it says concrete model may be undefined, or this is from the star import. So if you write something which is not a variable in your variable explorer, it will just tell you it is either undefined or it might be from the environment that you imported. You can ignore them, just make sure that it's not, you don't have an undefined variable. Now, if I run this, this will create me an empty model. Now, let me go to this. This is the model that we have. We have two decision variables, right? Now, what we are going to do, we're going to create the decision variables and then the objective function and constraints. The first step, model dot, hold on, I'm going to add something. What is the name of the thing that we want to add? It's x1, decision variable, equal to, what's the type of the thing that we want to add? It is a variable. Now, if you just write this, you can see there are lots of information from help that you have. The type is a variable. Now we have to make sure that the domain is given. In our model, x1 and x2 both are non-negative real decision variables, right? So I wrote none, and you can see from the list, I can select this one. Now, I'll run this too, okay? Oops. Okay, domain was not correctly written. Now it gives me. Do you remember that we could use print to print something in Python? In Pyamo, pprint prints whatsoever you have regarding a model. If we just print the model that we created and run this, this gives us pprint model. It gives us whatever we have regarding the model in the that we created. So if you have a model, if you have like decision variables, if you have like constraints, etc., pprint gives us information about the model that we have. So it's not, it's model.pprint. Now it works. So it gives us information of the model. So here, it says that you have this model which has one decision variable, which is called x1. This is what we want to see because we only created one decision variable, right? I will continue adding the second decision variable, and then I will p-print it to see what we see. Model dot x2, what is the name of the thing that we want to add? It is x2 equal to, what is the type that we want to add? It's a variable. Now, within, I will use, and non-negative reals. If I run this and p-print the model, you can see now, there are two variable declarations. One is x1, the second one is x2. When you add the objective function, when you add the constraints, when you add other stuff, again, you can p-print and see what sort of things, basically, how many decision variables you have, how the constraints look like, how the objective function looks like, basically. So we're running out of the time. I'm going to stop here. We'll continue solving this one and other examples in the workshop. Don't forget to bring your laptops and computers for the workshop. And please have Python IDE installed in your computer so that you can work with me. I'm going to stop here. I will stay here and answer your questions. I won't stop recording, so the questions also will be, questions and answers will be recorded as well. If you have anything else to do, you don't have to stay here. You can just leave. If you have any questions or you want to hear the answers, stay with me. Great. Let me go to the questions. Yes, domain was wrong, that I corrected. That was the, why can't we create a linear function and if function to solve the problem? It is because regular functions cannot deal with inequality. I'm not sure if I understand. Why can't we create a linear function and if function to solve the problem? It is because regular functions cannot deal with inequality constraints or require the specific input to work out a result. Are you asking about like system of equations? If that's the thing, system of equations, they don't have an objective, right? Well, the whole thing that we are doing with optimization is because we have a feasible region. And in the feasible region, we want to find the point or the points which optimize the objective function, right? That's why we are using optimization. What's the main difference between domain and within? Nothing. They are exactly the same. Domain and within are exactly the same. So you can use domain and within interchangeably because they do the same. And for both of them, you need to use any predefined domain that's in the within or in the table that I shared with you. Receiving as error message, module not found. If you have this error, module not found error, no module name Piamo. Piamo is not installed in your computer. So if you do pip install Piamo, you either get it installed or you will get something like this, the requirement already satisfied, okay? If it didn't work, depending on which sort of ID you have, there are different ways of adding Piamo. Can you tell me which, what is your ID that you're using? Did you use pip and it didn't work? How do I know when linear programming problem has more than one optimal solution when I'm using GLPK in Python? There are ways that, so you don't have to know, right? In reality, do you really need to know when you solve a problem with Python? Do you need to know if you have multiple optimal solution? It gives you a solution. The optimal objective function value is given to you, which is something that is calculated. But do you really need to know if there are different points? It gives you one point which satisfies all constraints. Perfect. There are ways that we can set a parameter and ask Python, Piamo, to tell you if there are like multiple solutions. And then it gives you a solution pool. It can't give you all solutions, right? Because the problem that I showed you last week was in 2-dimensional space, but then you have like 1000 dimensional space. How you can get multiple? It's not a line anymore, right? It's something that's completely different. When you have multiple optimal solutions, you don't really need to know, to be fair. In real life, you just give the optimal solution, one optimal solution with optimal objective function value. Vishti, your issue is because you don't have Pyamo installed. Did you install Pyamo? Does within non-negative reals and bounds 0 none do the same thing? Yes, exactly. Perfect. I'll show you in the workshop that they do exactly the same. So within and domain are exactly the same. Bounds 0 none is exactly the same as within non-negative reals or domain non-negative reals. Okay, yeah, when you have Pyoma installed, it should work, right? If domain and within are exactly the same, or they're different things that they work with Python. So there is no, I don't recall if there is any difference. I always use them interchangeably as like bound as well, right? So they do exactly the same, and they're just different sort of using them. I'll just check to see. I'm pretty sure that they are the same. PM. Okay. A variable response domain within synonym for domain. I don't know why they are different. Why they did create two different things that they do exactly the same. They do exactly the same. Domain, a set that is a superset of the values they okay within synonym to domain. This is what the documentation also says. Who knows? Can you repeat, please? Yes, within non-negative reals basically says that your decision variable is non-negative and it is continuous. Bounds with lower bound of 0 and upper bound of none basically gives you all decision variables which are greater than or equal to 0 and they're continuous. So bounds 0 none is exactly the same as within or domain non-negative reals. Because as I said, when you have a decision variable, Pyamo by default presume that it is a continuous decision variable unless you define it otherwise, that it is integer. When you have a decision variable which is continuous and you create a bound, lower bound of 0, this means that your decision variable is greater than or equal to 0 and it is continuous. How are they different in terms of their use? But is this related to domain and within? Exactly the same. So documentation says that within is the synonym for domain. So they do exactly the same job. They are exactly the same. They use the same predefined domains, which are in the table that I shared with you, but they're just different way of writing them. So when we have to set a range at that time, so that's a good question. If you, for instance, you have a decision variable which is non-negative, okay, and it is continuous, perfect. You have another constraint in your model that we have in this one. x2 is greater than or equal to 0, and it is also less than or equal to 1. You can add this x2 less than or equal to 1 as a constant to your model, or you can, when you are defining x2, you can say that the bounds are 0 and 1. This way, you have a range for your decision variable, which is defined as a part of defining the decision variable rather than creating an extra constraint. Does this make sense? Okay, fantastic. Any other questions? Do you have any other questions? Because it is recording, I don't want to just say it when you are just watching the recording. It will be funny. So it would be nice if you have any questions, ask it. Otherwise, either stop recording or I will end the lecture. Okay, fantastic. Objective function 12. Objective function. Oh, you solved this problem. I'm not sure. Okay, I'll have the code here. I can run it, right? 3 maximize. Okay, it is 8. If I run this, yes, you can see the solution, right? It says 12.5 is the optimal objective function value. X1 is 3.5. Y or X2 in my code of 1. I will solve it during the workshop, so can I please repeat the answer for this question? I'm a bit confused. So if I go to the model, we said there are different ways of defining the decision variable, right? What you can do is you can use within or define. Both of them do the same job, non-negative reals, right? Or alternatively, I could go with this x2, and rather than within or domain, I will give the bounds on the decision variable that I have. What decision variable is non-negative real, right? I said when you create a decision variable, Piamo by default treats it as a continuous decision variable. So you don't need to say it is a real number. You just need to say that it is greater than or equal to 0. When a variable is greater than or equal to 0, what is the lower bound that it can get? It's obviously 0, right? What is the upper bound that it can get? There's no upper bound on it, so none. This is the way that we use bounds to create a decision variable. The question says, what if I know that x2 cannot be greater than or equal to a certain value? For instance, there is another constraint which imposes that x2 is less than or equal to 10. Rather than adding a constraint, model dot constraint equal to constraint, and then expression equal to model dot x2 less than or equal to 10, what I do is I just add an upper bound on the value of x2, which is 10. So I would get rid of this, right? So if there is a range, you know that your decision variable should be non-negative, obviously, so the lower bound is equal to 0. If there is any upper bound, you can add. You will add it rather than adding it as a constraint. What is the output? What output will be there in case of there is an invisible region or unbounded optimal solution? It's not unbounded optimal solution. No, it's unbounded feasible region, which leads to unbounded LP. When you have unbounded LP, there is no optimal solution. So you will get unbounded LP or infeasible LP when it happens. Okay. Did I answer your question? Any other questions? Do you have any other questions? Okay, if you don't have any other questions, I'm going to stop recording first, and then I'll say goodbye to you.